Hi, my name is Ahmad Berami. Together with Tian Li, we will present Tilted Empirical Risk Minimization term, which is joint work with Mazia Sanjabi and Virginia Smith. Empirical risk minimization is widely used in machine learning, where you optimize a parameter to fit the average of individual losses. In this linear regression example, this would be the purple line. Empirical risk minimization has many practical shortcomings. It can overfit outliers and lead to solutions that are not robust. For example, when these few left-hand side samples are known to be noisy outliers. It can also underfit outliers and learn solutions that are unfair to subgroups. For example, when these few left samples are individuals from a different subgroup that we would actually like to serve. Motivated by exponential tilting in large deviations theory, we introduce tilted empirical risk minimization, which is an extension of ERM with an additional tilt hyperparameter t. Term recovers ERM for t equal to 0. And it highlights outliers to promote fairness when t is positive, and it suppresses outliers to promote robustness when t is negative. So here is the term objective, which recovers average loss and traditional ERM for t equal to 0. This is the purple line for this example involving 3 individual loss functions. When t goes to infinity, it recovers the max loss, and when t is negative infinity, it recovers the min loss. For intermediate values of t, it provides a smooth transition between min loss to average loss to max loss. As t increases from 0 to infinity, term solutions trade off average loss, which is the purple line, for max loss, which is the red line, which is a surrogate for fairness. Also, the loss variance across samples decreases, which implies solutions will generalize better to unseen examples. As t decreases from 0 to negative infinity, term solutions trade off average loss for min loss, which is the blue line, and it's a surrogate for more robust solutions. Term solutions approximate solutions of quantile losses. Kth quantile loss is defined as the kth largest individual loss. For example, the n over 2 loss is the median loss, which is useful in practice to promote robustness. As t ranges from negative infinity to infinity, term solutions effectively approximate the k-loss solutions for k ranging from 1 to n. In this example, from min loss to median loss to max loss, where median loss, which is the solid orange line, is hard to optimize, especially in large scale problems, as it is non-convex and non-smooth. We prove all these properties rigorously in the paper. Next, Tian will tell you how to apply term to large-scale learning problems in practice.
So term can be solved using simple extensions of widely available batch and stochastic solvers for ERM, and we provide rigorous convergence guarantees in the paper. And term is widely applicable to a broad range of machine learning problems. And with negative t's, we have experiments for outlier mitigation, robust regression, and robust classification. And for positive t's, we provide experiments for handling class imbalance, fair PCA, and variance reduction for better generalization. And we also show that we can use tilting at different hierarchies to achieve both fairness and robustness at the same time. And in the experiments, we show that term is competitive with or outperforms several state-of-the-art application-specific baselines. And next, we're going to discuss a couple of the examples in more detail. In crowdsourcing, having 80% of the labels being produced by low-quality annotators will dramatically decrease the test accuracy. And by applying term with negative t's, we see that we achieve the same accuracy as Gini ERM, which is an impractical upper bound that is training the model by removing all the noisy samples. And term also outperforms one strong baseline on this specific problem. And positive t's can promote fairness in terms of representation disparity by upweighting the underrepresented groups. And here we explore the problem of fair PCA, where the goal is to learn a projection that achieves similar reconstruction errors across the two subgroups. And if we use standard PCA, we see that there is a large gap between the errors on the low education and high education groups on this credit data set. And term can recover a recently proposed min-max fair solution with a large T, while at the same time offers more flexible trade-offs between performance and fairness by encouraging fairness in a less aggressive way. In terms of future work, it will be interesting to investigate other applications and properties of the term framework to study the generalization guarantees of the objective with respect to T, and to investigate further connections between term and other risks, such as distributional robust optimization, conditional value at risk, and so on. Our paper and code are available online. Please check it out if you're interested. Next.